Good morning, young friends. How are you? I am sure all of you are taking outward rest and care against and COVID 2019. As we know, every challenges are an opportunity, and this challenge really is the biggest against humanity. We took this opportunity to strengthen our online sharing of the knowledge with our near and dear students. Today, I am delivering first lecture on vibrational spectra of diatomic molecules. In our paper, Atomic and Molecular Spectra, this stands importance not only in terms of exams but also in terms of wide applications. In almost everywhere in understanding details of materials and development of their applications. In this unit of syllabus, we shall learn about vibrational energy of diatomic molecules, diatomic molecules as simple oscillator, its energy level diagrams and spectrum. We will also study Moore's potential energy curves, molecule as vibrating rotator. Interestingly, here we will discuss how these two vibrations and rotations can be clubbed, as we know that in real practice we cannot separate them from each other. Vibration spectrum of diatomic molecules, PQR branches, infrared spectroscopy, laser semiconductors, laser diode, vibrational Raman spectroscopy, structural determination from Raman and IR spectroscopy will be studied here. The aim of this unit is to provide knowledge and understanding about diatomic molecules, their structure and interaction of energy. We will also understand origin of vibration spectra, basic principles of infrared spectrometry, and Raman spectroscopy. This will also help us in learning structural determination from Raman and IR spectroscopy. What first bring in your mind when you hear the word diatomic molecule? This is one of the most important class of the molecules. Yes, the di is a Greek word and it means two. So those molecules which composed of two atoms falls in this category. Now the query may arise, atoms of same or atoms of different species? Yes. So my comment is both. Both are diatomic molecules. However, most of the diatomic molecules are of same elements. And yes, Of course, though few combine with different elements also. On the basis of this is termed as homonuclear or heteronuclear. Something very important to note here. At room temperature, virtually all diatomic molecules are gases. Now, think over some examples. Yes, H2, O2, Cl2, and so on. All are gases. Interestingly, some substances at room temperature also give crystalline property. However, they become diatomic at higher temperature, which is not a property at lower. As we told in previous slide, homo means made up of same atom or elements. If a diatomic molecule consists of two atoms of the same element, then it is said to be homonuclear. And the examples are hydrogen, oxygen, or others. But we must remember that the bond in a homonuclear diatomic molecule is nonpolar. I hope you are aware of polar or nonpolar. As both atoms are same in homonuclear, they have same power to attract their electrons, and so covalent bonds are formed. And this property is responsible for many interesting behavior of the diatoms. Another category is also there, that is heteronuclear. If a diatomic molecule consists of two different atoms, the molecule is said to be heteronuclear, such as carbon monoxide or nitric oxide. The bond in heteronuclear diatomic molecule is always polar. Polar. Why? Because both atoms have different electronegativity or electropositivity. So one have more power to attract electron than other. As we also know, this is called ionic behavior of bonds. Diatom also have several classifications. One of them is diatomic elements. Diatom of hydrogen, nitrogen, oxygen, and halogens like fluorine, chlorine, bromine, iodine have same nuclear structure. However, there is a difference stand out with nitrogen. Its atoms share a strong triple bond. This makes nitrogen very stable substance. As we know, it found in atmosphere in a large proportion due to this. Very interesting thing to remember here about the sum of the elements. called noble gases such as helium, neon, they are rarely form molecules at all. They are monoatomic. There is another class of diatomic elements. Other diatomic elements have metallic nature. In these, electron sharing is easily possible, and most of the elements are crystallizing also at normal temperature and pressure. They do not form molecules, while they do form molecules with nonmetals, such as cupric chloride, ferric oxide, and many molecules. Few compounds, such as carbon monoxide, hydrogen chloride, and nitric oxide, have diatomic molecules, like diatomic elements. These compounds are gaseous at room temperature. Chemists call these compounds heteronuclear because their atomic nuclei come from different elements. Another class also exists of diatomic molecules at higher temperature. At room temperature, some elements like lithium is solid and doesn't form any diatomic behavior. However, if you heat it up such that it becomes gas, the gas phase is a diatomic molecule. This is known as dilithium. Other elements that also form diatomic molecular gases includes sulfur, sulfur formed disulfur, tungsten formed ditungsten, and carbon dicarbon. Similarly, ionic compounds such as sodium chloride, they are not diatomic at normal temperature, can become diatomic when turned to gas. So it's an interesting story about diatomics. Diatomic molecules at low temperature is also have many interesting qualities. Oxygen, nitrogen, and other diatomic molecules, they give gaseous behavior at room temperature. But if we decrease the temperature appreciably, then the forces become weaker and atomic bonds attracts neighboring molecules. This allows them to enter a new state that is called liquid state at low temperature. Liquid nitrogen, liquid helium, we also know these words. And these have many applications in science. Diatomic molecules gives good vibration spectra and have applications at various places. But before learning the insight of vibrational spectra, we must review the classification of spectra and origin of spectra. Spectra originate when we supply some energy to the materials. When we apply some energy, it converts in the form of various spectra: absorption, emission, transmission, as per their behavior. Two ways to explain the behavior of molecules. One is either by studying wave functions, as we do in quantum mechanics, and second way is study spectrums. We all know that the wave function describing the energy bands of atoms and molecules are more complex than spectrum studies. It is difficult to analyze. So, we must study spectrum for most of the molecules. We must realize that analysis of molecules can be done by study of matter with radiations, and here of course by electromagnetic radiations. In spectroscopy, we study the interaction of electromagnetic radiations with the materials in concern. We supply energy of various wavelengths and study of interaction behavior of atoms and molecules at specific wavelengths or frequencies. We study the output in terms of transmission, absorption, and emission. Whether the radiation will be absorbed or transmitted or some emission will be there, everything depends on characteristic of the material. This is very important here. In diatomic molecules, we have three types of transitions occur due to interaction with electromagnetic spectra: electronic, rotational, and vibrational. Why electronic? Because the diatomic molecule is made up of atoms, and atoms consist of electrons. Whenever we strike radiations, electrons of these atoms gives electronic spectra. Rotation and vibrational spectra due to molecular behavior. As seen in the figure, here two possible rotations of diatomic molecule shown. The molecule can be rotated about the axis or perpendicular to the axis. Similarly, diatoms also give vibrational spectra. It can vibrate from their own position, like a spring. As it's shown here, difference in energies of these spectrum. The first one is electronics levels, in the middle vibrational levels, and then the right rotational levels. Electronic spectra has highest level energy level difference, and each level have some vibration level associated with. Similarly, each vibration level associated with some rotational levels. You can see here how the energy difference matters here. For electronic, 10 to the minus 19 joule. For vibrational, 10 to the minus 20. And for rotational, 10 to the minus 23. It is continuously decreasing. The detail will be continued in the next lecture about vibration spectra. For reference, you can use the following books for further reading. Most of the time, I am following C. N. Banwell and M. McCash. Thank you and take care for you and your family in such unforeseen conditions. Bye.